here is the next edition of notes. So here's your introduction to the newest unit, and this is really a small extension of what we've been doing. So we're continuing to talk about how things move. Why things move. So we're talking about all the forces that act on things. And what we did before is everything ended up balancing out. So if you added all the forces up, they canceled. Well, now we're going to talk about the question, what if they don't cancel out? How does that work? Well, let's go ahead and compare the two. If we have balanced forces, then all the forces will cancel, which means if you added them all up, let's say we had 100 forces acting on something, they would cancel out to be 0. So in our force diagrams, if we had something going up, down, left, and right, the two going up and down cancel, the ones going left and right will cancel. Well, if they are unbalanced, then they will not all cancel. So if you add up all the forces, you will have some total force somewhere, and what we call that is F net. This is the net force, and it's also called the total force. Let's do an example. So we're pulling a box across the floor, and we're pulling with a force of 10 newtons, and the friction is not 10, so the friction is less. So we have 6 newtons resisting it. Okay, our mass is 3 kilograms. So we're going to do the same thing we've always done. I'm going to draw a force diagram, and we're going to fill out the things we know that are really easy. Mass of 3 kilograms. We have 30 newtons of force down. So this is it's not moving up or down at all. It's just moving across the floor left and right. So that's going to be 30 on both sides. And then we continue to label everything else. We got 10 to the right and 6 to the left. So our net force is just going to add them all up. And we have 10 to the right. I'm going to make that positive. 6 is in the opposite direction, so that's going to have to be negative. So our net force is 10 minus 6. We have 4 newtons of force total to the right. So the question is, what happens if we have a net force? Let's do one more example real quick. We've got a box on a hill, but this time it's accelerating down. Alright? So that's what happens if we've got net force somewhere. We've got an acceleration. So, drawing the force diagram, we have an angle of 30 degrees, mass of m. So we can figure out everything else, just like we always have. Excuse me. Okay, so I'm going to draw it just like I've always done. We got 50 kilograms. That means we have the force of gravity is 50 newtons. We know that some of the forces will cancel here and some will not. Let's say we could measure this frictional force. Let's say we measured friction to be 20 newtons. And my question is, what's the net force going to be? Alright, so when we look at our diagram, those two components will have to cancel. And the other two, so this one and that one, they will not cancel. One of them will be bigger than the other. Let's redraw it over here. So we've got 30 degrees, 50 newtons here. We can calculate the rest of that triangle and try to figure out all the forces. So those two are the same, normal force and that component. Let's give them names, y and x. So y will cancel with normal force, x will not cancel with friction, but we have to add them up. So we can find our normal force just like this, where we've got using the cosine, and then solve it for y. That'll tell us normal force. It's 43 newtons. If you don't believe me, put it in your calculator. Now, what is our net force? Well, it's going to be x minus this. We've got x going in that direction. friction going in the opposite. So our net force is going to be friction, or no, excuse me, X minus friction. Okay, so if we add those up, we have the net force. But what we got to do is we have to find X first. We can do that easily with the triangle. We can just do sine of 30 times 50. That'll give us X. And if you remember, well, if you were in class, if you remember, sine of 30 is 1/2, so X is 25. So our net force is 25 minus what we were given, 20 newtons. Our net force is 5 newtons, and that is going to be that way. So down the hill. 5 newtons down the hill. Okay? So here's the grand idea. If there is a net force acting on an object, alright, so if it's not 0, everything doesn't cancel, then that object will accelerate in the same direction as the net force. And this is what it will equal. This is our equation we're going to use a lot with this unit. So the net force is equal to mass times acceleration. Mass times acceleration. Alright, eventually we'll be doing a couple of activities in class where you can actually verify this with a lab, or verify it experimentally to show those 3 variables are related all in that way. Alright, to do these problems, the only thing that's different is in your force diagrams, not all the forces will cancel. So you're going to have less equality marks. But you're still drawing the forces just like they always are. But they're going to total up to some net force. Okay, so let's compare what we used to do. If there's a net force of 0, then we can conclude that object is at rest or is at a constant velocity. If the net force does not equal 0, then that object is accelerating. And you can flip-flop this. If we know something is at rest or at a constant velocity, then we can conclude that there is a 0 net force. And if that object is accelerating, then we know there is a net force not equal to 0, and that it equals mass times acceleration. All right, we're gonna do this next part in another video, but this is the grand conclusion here. If there's a net force, there's acceleration. If there's no net force, it's at rest or at a constant velocity. All right. When you come back to class, we're going to do some more examples together, and you will be able to calculate more complicated examples of net force. I will see you in class.